Let's go to Liquid 862 shortest subarray with sum at least k. For this question, it gives us integer array nums and integer k. And let's find the shortest subarray with a sum at least k. If no such subarray, return -1. So we'll see there may be positive, negative values, right? Um, So because there is a negative value for it, right? So we know if there is, it is all of the data is positive, it will be very simple because those kind of subarray will be monotonically increasing. We just use two pointer, left pointer, right pointer, and keep a shrink, right? And trying to see in any for every right pointer, and then if condition is satisfied, shrink the left pointer, and find a local length compare with global length, right? But there is negative means those kind of sum is not necessarily monotonic, not necessarily monotonically increasing. So we need to think about some other way, right? Let's thinking about this in brute force way, that if we iterate um, right pointer, left pointer, right pointer. So this will be O n square time complexity, right? And if we calculate values from left to right, it will be n O n power 3 time complexity. We find all of these combinations and find our shortest subarray. Apparently, this kind of time complexity will not be good. So the first optimization is that we can use a prefix sum, right? Pre-calculate the prefix sum, and then brute force to iterate the left and the right, right? So we can go from n power 3 to n power 2, right? Because it is still brute force about the left and right pointer. And we pre-calculate those kind of prefix sum. So it will be O n square time complexity. It is better, but still not good. So let's think about another way, right? So we know if we already calculate the prefix sum already been calculated, we iterate those kind of right pointer, right? And if we have some way to calculate the minimal previous prefix sum, right? We can um, calculate those kind of subarray um, from this minimal to right, right? And we know as long as this kind of right to this minimal, they are greater equal to k, right? That means this will be one of our candidates. And in the and also we can when we iterate this kind of right, and we can try to shrink this left pointer, right? Because the minimal, when we shrink this kind of minimal, can be always being greater, right? Because this in this range, those kind of minimal previous will always being greater because it has small data, right? So for example, we use if we have we can get the minimal prefix sum efficiently, we can do something better, right? So how can we get the previous minimal prefix sum. Intuitive way we thinking about is that we can use some kind of heap, right? Or tree set. Because we need to delete index, right? So this kind of heap we can use some kind of lazy deleting. And in this case, we can get rid of our time complexity because we use a heap from n square time complexity to n log n time complexity, right? And as long as this right minus the minimal heap is greater equals to k, we can shrink our left pointer, right? Of course, the left pointer is actually pointing to the minimum one, right? We can shrink our left pointer. So this will be our improvement, one of our improvement, right? But we'll see monotone heap is better to calculate a top k in a slide window, right? But for this question, it's just want to find the minimum in our previous slide window, right? So do we have better approaches? We know monotonic queue is used to get the minimal or maximal value in the sliding window in O n time complexity, right? And for this one, um, um, if we can do monotonic queue way, right? It is um, it can help us to get the minimal or maximal window in a value in a sliding window for the prefix sum, right? So how can we do monotonic queue? So let's look at our approaches. So if let's say when a right index is coming to our data structure, let's assume there is a data structure, right? If the prefix sum of this kind of index, for example, J, right, or right, is smaller in than the prefix sum which is stored in our data structure, right? That means when we calculate the subarray later, the previous one will never be an optimal solution because this one has a smaller prefix sum and greater index, right? So that means those kind of lengths will be shorter. And it is more possible it is greater than length k, right? Because we are trying to find the smaller prefix sum. In this case, that means when we store those kind of data, we don't need this anymore because this one has greater prefix sum and a smaller index. So when we calculate for the future index, this will never be an optimal solution. So in this case, we can safely remove this kind of prefix sum. Uh, so 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 that means if there is a prefix sum is smaller and coming later, have a greater index, right? We can pop out those kind of data structure which has greater prefix sum and a smaller index. But the thing is that if in the previous one, it has smaller value, right? Even smaller prefix sum and a smaller index, we still need to keep it because it is possible in the later part we calculate the prefix sum difference is greater than k for this kind of candidate. So we cannot delete in the previous prefix sum, which is smaller value, right? So in this case, in our data structure, we'll find it is always keeping some kind of prefix sum in a increasing order, right? So it is some kind of monotonic data structure. For no matter it is monotonic queue or monotonic stack, right? We are always pushing our index to our data structure. And before we pushing, you will see now so the process is that this prefix sum, if it is smaller, right, it will keeping popping this, and this one is smaller, right? Then we are able to put this one here, right? I get rid of this, get rid of this. And before we put this index to our data structure, we can calculate from its top, right, to this one, to this index we pushing. We calculate on its left. So if this index, for example, J with the peak on the left, right, this one means it has the smallest prefix sum in this kind of window, right? So if we have this kind of index, prefix sum, right? This kind of prefix sum here, minus prefix sum here, right, is greater or equal to k. Then it can be one of our local candidate, right? And also this has been calculated, right? We can safely pull the data from the left as well, right? Because those on the right, if they are pushing into a queue, you have a longer index, right? So we'll not calculate the later one, right? So this will be our candidate. We can also keep him pulling from the left to get our local result. And those kind of local results will compare with our global result. Um, and um, and so um, that is also, so putting from the left. This is like the sign window, right? This is our right pointer. This is our left pointer. As long as this right pointer prefix sum minus left pointer prefix sum is greater or equal to k, we are able to pull those kind of things, move our left pointer, right? And here, every time we pull out data from our left side, we need to have a local result compare with our global result. We cannot compare when all of this being pulled out, because the index in our data structure is not necessary to be consecutive. So every time we pull out a data, we should compare with our global result. So doing like this, because every prefix sum, we calculate the prefix sum first. This is O(n) time complexity, and every prefix sum is in-queued once, and we'll go to the queue and either pull from the right or pull from the left. Well, pull out from the queue once, so the time complexity will be O(n), right? And we need a data structure can be pulled from the right and left. So that is a deck data structure. And the space complexity will be O(n), right? O(n). The worst case is that it is some kind of monotonic increasing, put all of the data into this kind of data structure. And only the largest one and the smallest one is greater than k, right? Or we don't find any. So space is also on. So let's write code for this. Um, so we have int equals nums dot length, and we use no matter we use brute force or use the lazy delete heap or tree set, right? We need to use a priority queue, use a prefix sum, right, to optimize it. So let's calculate the prefix sum first. Um, here, because this kind of data have length 10 to the power 5, and the number will also be 10 to the power 5. So let's use a long, right? So that will be more safe for the kind of range. So what we write is for int I equals 1, I smaller than n plus 1, I plus plus. So we're going to have a prefix sum I equals the prefix sum I minus 1 plus nums I plus 1, right? So we know we use deck. We put in this kind of data structure that is the index. So deck equals new array. Right? And we need a result, right? Result should be, let's say, integer the maximum value. Okay. So what we do is for int I equals 0, I smaller than n plus 1, right? We are iterator in the prefix sum array. Um, so this I plus 1 in the I plus plus. So here we do the monotonic queue is that we are write while this kind of deck is not empty. And if we have a prefix sum deck dot pick, right? If this one um is greater equal to greater deck is pick last, right? If this one is greater equal to prefix sum I, that means in the previous one, this one will be longer subarray, and it's less possible it will be greater sum, right? So this one will not be any useful anymore, right? Because we'll never compare with this index anymore. So in that case, we can safely uh, pull this index. So we can have that pull last, right? Here, this while loop is the two pointer while loop. That is why this deck is not empty. This is for its left pointer. This I is it's a right pointer. We can also write right, right? And prefix sum I minus prefix sum deck. Let's say pick first, right? If this one is greater equal to k, right? Then we can move our left pointer. So we'll say every time we move our left pointer, we should update our result equals next dot name result. We cannot put this update outside of the while loop because we'll see in this kind of data, because we pull last those kind of data in our data structure, the index may not be consecutive anymore, right? So for every index, we need to compare the result. And so that will be our current index, right? So this is right pointer minus deck dot pull first. And we'll see for any monotonic queue or monotonic stack after this while loop, right? We should always um, push the index. So we'll have deck pull offer last, right? Offer or add last, offer last, right? So, um, so what we are going to return result. If it doesn't go to this while loop, right, means there is no subarray satisfy our conditions. So the result will be integer maximum value, right? So if result equals integer dot max value, we are going to return -1. Otherwise, will be our result. Right? Integer max value. And we'll also write a Python code for this. So we need to pre-process get the prefix sum. So let's get prefix sum array. Let's get this length out. And we're going to have prefix sum equals this one multiplied n plus 1. And for I in range n plus 1, right? Let's write 1 to n plus 1. Prefix sum I equals prefix sum I minus 1 plus nums I minus 1, right? And we'll have a result equals float line f. Okay. And what we do is for the things that we need use import, right? Import from collections, import stack, because we want to use stack, right? Here, that is two pointer for I or right in range n plus 1. This is right pointer. So here, this is part of the monotonic queue is that deck is not empty and prefix prefix sum I is small equal to prefix sum deck -1, right? It's a peak. Then we're going to have a deck top. And here this while loop is the shrink. We can keep it shrinking the left pointer to move it to the right, right? Shrink the window size. So as long as this one is satisfy the condition predicted some deck 0, right? Is greater equal to k, then we can keep moving the left pointer. So that is our result equals mean dot the result I minus deck top left, right? And uh, here, this for loop and this while no matter it is monotonic queue or monotonic stack, after that, we need to add a index I to our deck, right? So we need to have a deck append I, right? So in the end, what we return result equal result and equal to float IF, right? Else minus 1. While prefix sum in the prefix sum, I am equal to we didn't define this yet, right? Let's call it the we need a let's do this dq equals that uh, and we call dq and dq pop dq